Okay, class, we're back. For some reason, the little app stopped collecting video, so I'm going to pick up hopefully where I left off or close to it, and then there'll be more than one video for the lecture on 323. You'll click on one when it runs out. Click on the second. I'll annotate them so that you'll know to do so. Maybe I can concatenate them if I'm smart enough. Probably not. So again, right, here's this array of isotropic point sources, right? Point source 1, 2, 3, down the array. These are the rays out to the observation point. So we're looking in the direction theta, and we want to know in that particular direction how these sources add up, right? In the direction theta, what is the amplitude of the superposition of the fields from each one of these isotropic point sources, right? So if you look here, right, notice that this is our reference, right? The fields out in that direction from element 2, this is element 1, this is element 2, have to, they will actually lead the fields from element 1 by this distance right here times the phase constant, right? What is the phase constant? That's beta, right? And so beta has dimensions radians per meter, and so if you multiply beta by this distance right here, right? What is that distance? It's d cosine theta, right? Here's the right triangle. This is d, this is the angle theta, right? D cosine theta is this length. And so if you multiply d cosine theta times beta, that'll give you the amount of phase shift by which this element leads this element in propagating out to the observation point, right? So that's what I'll refer to as a propagative phase shift, right? And so this element, right, it's going to lead the reference element by beta times 2d times cosine theta, right? Because this distance, I take d and add it to d, that's 2d, multiplied by cosine theta. That gives me this length. I multiply that by beta. That gives me the amount of phase shift by which the third element in the array leads the first element, right? Spatial phase shift, right? There's also electrical phase shift that we can adjust, right? Alpha. And so the total phase shift associated with the sources at the observation point is the sum of the spatial phase shift, the beta times distance phase shift, plus the electrical phase shift, right? So this is caused by some phase shifter associated with the feed line that goes to that particular element. Okay, so page 1. Let's move on. So next thing, right, let's add up the response from each one of these to get the total. Right? So we can do that mathematically. It's pretty straightforward, in a straightforward manner. So let's add up the fields from the isotropic point sources and learn how to sketch their far field pattern. Okay, so this is what we're going to call the array factor. It's just the sum of the contribution from each source. So in this case, source 1 has strength. They're all going to have strength A sub 0. And when we normalize, that's going to go away in a minute. Right? So the first one is just 1, A sub 0. The second one is A0 times e to the j psi. Right? What is psi? It is the sum, right, of the spatial phase shift and electrical phase shift for element 2 in the array, right? Don't forget, this element leads that one electrically by alpha. It leads it spatially from a phase shift standpoint of d cosine theta times beta. That's how much phase shift this element will have that's how much this phase shift, the element, the phasor associated with this element will lead the phasor associated with that element in the direction theta. Okay. Beating a dead horse there, but I want to make sure you understand that. And then, right, the next element will have twice that phase shift on down the array. So there's going to be this will sum up to n minus 1, right? Since that one doesn't have an index, it's going to be n of these. So, right, so psi is beta d cosine theta plus alpha, alpha spatial phase shift plus electrical phase shift. So we can manipulate this thing. If we take the array factor and we multiply it by e to the j psi, we get equation 2. If I subtract 2 from 1, right, do the arithmetic, you're going to get an expression that looks this way. So then I can solve for the array factor by just taking, doing the algebra here and dividing this side by 1 minus e to the j psi. Okay. Then I'll do a little manipulation, right? I'm trying to manipulate this thing so I can get something that looks like a sine, right? E to the j something minus e to the minus j something is close to sine if I just divide by 2j, and similarly in the denominator, so the 2j's will disappear. And so in so many words, then the array factor has this form. So this is the phase shift, which we're not interested in particularly, right? We're primarily interested in the magnitude of this function, right? So in most cases, but not always, right? Certainly there are cases where you're interested in the phase. In most cases, we ignore the phase factor, this right here, yielding the array factor of this form by just dividing that out or just taking the magnitude of it, essentially. So the array factor, right, this is a sine x over x type function, right? It's a sinc looking thing. And so the array factor is going to be a max when psi is 0. Right? So if you evaluate this, right, if you evaluate the array factor when psi is 0, you can come back up here and put psi is equal to 0. That's 1 plus 1 plus 1 plus dot, dot, dot. That's just going to be n. There's going to be n. That will equal n. And so the maximum is n times a0, the maximum value of this. And so that makes sense, right? Because if you have n elements, each of strength a0, the biggest it can possibly be is n times a0. That's the position in space where they're all adding in phase, right? So we can normalize this and we get finally our normalized array pattern or our antenna pattern for the array. So that puts an n down here in the denominator. So this is the function that we're going to study. Sine n psi over 2 divided by n sine psi over 2. Where psi is what? It's beta d cosine theta plus alpha, right? This is spatial phase shift. This is electric phase shift. So depending on, right, our spacing in wavelengths, that's the only thing that's going to matter is the electrical spacing between elements. And the electric phase shift, psi is going to have a different value. And so consequently, right, our pattern is going to have a different value. All right, so hopefully that makes sense. And you can review this. It's straightforward arithmetic, right? Just summing that series. But you do that kind of thing all the time in signals and systems. So presumably you're accustomed to it, right? And this is, right, keep in mind what you've got here. This is if you like the terminology, this is a sampled system, right? If we had a line source, this might be a continuous variation of source, right? But these sources are discrete. So you expect to get some of the similar sorts of things that you would get when you have a sampled system in signals and systems, right? And you're going to see that. momentarily if you remember from sequence. Okay, let's see how this works, right? We're trying to plot the pattern of an array of isotropic point sources that are equally spaced, have equal amplitude, and have a linear phase taper down the array. That's the objective here. So, right, whenever psi is 0, psi will be a maximum equal to unity, right, because we normalized it. F of psi is periodic with period 2 pi, right? It's a spatially sampled function. So what we want to do, we want to plot f of psi as a function of theta, right? We want to first plot f of psi versus psi, then plot psi versus theta. That's the technique we're going to use here when we're doing this in this back of the envelope graphic method. Okay, now there's nothing that keeps you from right. There's nothing that keeps one from literally programming this simple function up in MATLAB, right? You can do that. It's pretty straightforward. And maybe we'll do something like that. But for now, we're just concentrating on the graphic technique. Okay, so uh, what do we? So we want to plot this as a function of theta. So the technique here is first plot f of psi versus psi, and that's going to depend on what n is, right? It's going to depend on the value of n, right? Because if you look at this function, right, f of psi versus psi depends on n. So if I tell you what n is, then you could write a MATLAB program and plot this function for a given n. So you're going to want to know, or n has to be essentially specified. So, right, this gives us an easy way to plot the pattern of an array of an array of n isotropic point sources. So let's work a few examples and make some general observations. Okay. So let's do example one. Simplest as we can make it. So we're going to have two isotropic point sources separated by a half wavelength, and let's put them in phase. Okay. So step one, first plot f of psi versus psi, right, for n equals 2. And so for the n equal 2 case, right, it looks like this. Easy to plot. You can plot this in MATLAB in a straightforward manner, right? You would just be plotting, uh, sine of psi divided by 2 sine psi over 2 for values of psi between minus 2 pi and pi, and this would be the function that you would get. So now if I change n, right, obviously if I change n, this plot is going to change. But for now, right, we're just studying the n equal 2 case. N equals 2. Okay, so this is f of psi versus psi. Now, let's look at psi in terms of theta. Psi is beta d cosine theta, spatial phase shift plus electric phase shift. Okay, but beta, recall, is 2 pi over lambda, right? Phase constant, waves propagating out, times the spacing between elements, half wavelength. So the lambdas cancel, the 2's cancel, that gives us pi cosine theta, and then alpha is, these elements are in phase, right? So since they're in phase, there is no phase shift between them, or alpha is 0, or alpha is 2 pi, or 4 pi, or 6 pi, whatever you want to use. Might as well be 0. Okay. So psi as a function of theta is pi cosine theta, right? So it turns out that this right here is a circle, right, of radius beta d and center alpha, right? So it's the equation of a circle in polar coordinates whose center is at alpha and whose radius is beta d. Right? So that turns out to be important. So here's how we do this thing, right? So here's f of psi versus psi, right? So now I'm going to plot this circle, right? And so since alpha is 0, the center of my circle is going to be at psi equals 0. So I come down here along this line, and that's the center of my circle. The radius of my circle is going to be beta d, or the radius of my circle is going to be pi. And so when I take my compass, or I just sketch it for that matter, I come out a distance pi, and then I draw this circle. How did I know what the radius was? Because I knew the spacing. Beta times d, 2 pi over lambda times lambda over 2 is pi. So I know the radius of my circle is pi. That's why I came out this far and drew the circle, right? Now, theta, this is the line of the array, the z-axis. Theta is measured up this way. So when theta is 0, I just go up here to figure out what the value of the pattern is, right? In the theta equals 0 direction, I come out here, go straight up, and read it off of the f of psi versus psi curve. So in the theta equals 0 direction, the value of the pattern is 0. So I have a null that direction. As I increase theta, I'm going up here, I'm going up here. F of psi is getting bigger, so that when I'm at theta equals pi over 2, I'm at this position. And so in that direction, there's a main beam max. So I go from a null in the theta equals 0 direction to a main beam maximum in the direction theta equals pi over 2. Then as I go from pi over 2 to pi, right? So visible space is from 0 to pi. And so from 0 to pi over 2, I go from a null to a main beam max. From pi over 2 to pi, I go from a main beam maximum back to a null. And so I get that, right? This thing is the axis of symmetry is the z-axis, and so the three-dimensional pattern is just this pattern spun about the z-axis. And so this lobe up here is simply going to repeat down here. That's always going to be the case. So it repeats. And so here's my pattern, right? Voila. So we get the pattern of a pair of isotropic point sources, right, that are spaced by lambda over 2 as a function of theta. So maybe I didn't pull this down. Again, growing pains with the video, but again, right, here's our circle. Here's the center of our circle. Here's the radius of the circle, right? In the direction theta equals 0, the radius of the circle is pi, right? The center of the circle is at 0. In this direction, theta is measured up this way. In the theta equals 0 direction, I go up, that's a null. As theta increases, right, here's a higher value of theta. It hits the circle here, I go straight up, and so the value of the function is increasing. So as I go from theta equals 0 to theta equals pi over 2, the pattern value increases, and I just plot that in a polar sense when I use the radius of the circle as a reference for the maximum value. So it's a little confusing at first, but when you think about it, I think you'll see how this works. So let's do the same problem, right? N equals 2, right? Because it's n equals 2, I get this. This is my f of psi equals psi for the n equal 2 case, right? So, and then this time, let's put them out of phase, right? So this will be 1 at an angle of 0, and this will be 1 at an angle of minus pi. So this one lags behind this one. This one's negative and that one's positive. That's the way you think about it. So either plus or minus pi would indicate that this is negative, and you get the same answer as you can verify for yourself, right? So when we do psi this time, right, it's going to be beta d cosine theta. They're still separated by half wavelength, so it's going to be cosine theta